Okay. So let me see what I can do with this. All right, good, cool. So we're going to continue some of the discussion from last time and talk about how to deal with these augmented red-black trees, well, augmented trees in general. And I'm going to talk about a couple of different problems so that you get a better understanding of how to use these data structures. And so please jump in and ask questions, because I know, so who, were any of you there this Saturday to work out the competition problems? Who all were there?
I did it on Sunday.
Okay, oh, you did it on Sunday, okay. Anybody else?
I was there.
You were there, Clement?
I was there, yeah.
Anybody else?
There was Samara,
Okay.
and a couple others who aren't currently here.
Okay. All right. David, were you there?
No, I was not.
Okay. All right. But did you look at the problems, those of you who weren't there? Have you had a chance to look at the problems?
Yes, there was.
Si Adobe está como trabado, pero necesito.
What do you mean? Oh,
Adobe. No me deja
Adobe?
hacer nada.
Sorry?
Sí, pero what is
It's
this?
a background process, so it's
David,
running
you're
in the
on mute.
background.
Pero qué es lo que es?
No. Oh, sorry. I was taking care of something for my mom. Wait.
Okay.
So I did look at two of them. The first one about like helping the programming competition to make a program for the points for each team. That was very challenging. I did try it, but like I couldn't. I spent all my time like doing that one, but yeah, it was very challenging. I was trying to use what we saw like in the class, but yeah.
But were you able to get the basic data structure to work?
No, because I was trying to use the red black tree and put the rank, well, the size there, but I couldn't make it work. Yeah, unfortunately.
All right, let's see if we can make things a little bit simpler today. So we're going to talk about a couple of different problems, but before that, let me get past some of the basics. About the contest. Remember that this Saturday from 2 to 5, there will be a practice contest. The actual contest, of course, is a week after that, and it'll go from 2 to 7 p.m. And before 2 p.m., there are a bunch of ceremonies, and after 2 p.m., there are a bunch of ceremonies. So make sure that you have all afternoon for Saturday available for your time to work on these problems, but also to get registered, to understand the environment, and so on and so forth. You need to understand that you're going to be 3-person teams, and did you all get email from me about the teams you're in?
Yes.
Okay. So there are 3-person teams. Your emails are there, so you should be able to locate your team members. If you haven't, please email me and ask me. And of course, you already know that the competition goes from 2 to 7 p.m., so that's 5 hours. And there'll be about 10 to 12 problems. The more problems there are, the better it is for you, because your job is to find the easiest problems there and figure out how to solve it, okay? Our goal here in general is going to be to at least learn what the competition is about, so that next time we can be very, very competitive. I know some of you have some very good skills, but for others, if you're not able to solve a whole bunch of problems, this is not the time to be depressed about it. Your goal should be to solve one problem, and then If you're 3 people, you'll have 3 problems solved, and that would make you fairly competitive. Some of you may be able to solve more than one, but that's great. That would be bonus. So part of your job when you get started with the competition is to find a problem that's at your level, that uses your skills or your knowledge, and then figure out how to attack that. And if necessary, work with your teammates, talk to them, solicit some ideas from them, and then figure out how to divide the tasks so that you can then go at it. Often what happens is that you think you have the problem solved, you write the code, and it doesn't work. And at that point, you can stare at it and not make much progress. So that's a point where it would be good to use your teammates to help you and have them take a look at your code, tell them your logic and your algorithm, and see if they can spot the error that might be in your code. Or maybe there's some 1 or 2 cases that you haven't taken care of. So that's really what you need to do as a team. So you get to communicate with each other via Discord, and you get to divide the problems up. Of course, it doesn't matter who solves the problem, the team gets the credit for it. This time, all the submissions will be on a environment called Kattis, Kattis. I will send you some information about Kattis. One of the things you need to do is to set up an account there and register there on Kattis. So make sure you do that. Also, you should have received an email from the program organizers. Did any of you receive one? Looks like no is the answer. Is it? Lazaro, did you receive anything from the organizers from ICPC?
I'm looking through my email now. I believe not.
Okay. All
Yeah,
right.
no, same here.
Same there. Okay. All right. I'll check on this today and see why you guys haven't received that. All right. But they will give you instructions on how to register on Kattis and make sure that you are a valid competitor for the competition. Okay. So that's all I have to say about the competition. Let's move on to something else. All right. So remember, we talked about red-black trees, and a red-black tree is basically a binary search tree on steroids. So it has some extra stuff that makes it really good. And the part that's good about it is that the operations of search, insert, and delete can be performed in log n time. And that's what is great about it. It's in that sense, it's better than any of the other data structures because you're able to solve all the operations in very, very efficiently. After that, we looked at 2 more operations, one called the rank operation and another called the select operation. Remember, the rank operation presents you an item and says, what is the rank of this item in your data set? And your job is to figure out what its index would be if you put all the elements into a sorted array and you went and looked for this item. So that's called the rank. The select operation is exactly the opposite. You provide a rank and the select operation would return to you the item with that particular rank. And what we saw last time, was that, excuse me. What we saw last time was that we could do this rank and select operation in log n time. The rank and select operation, we are able to do that in log n time because we augmented the red-black tree, or we augmented the binary search tree. And the way we augmented this is shown on this slide. Remember that every node in a binary search tree contains a key value, contains a left pointer, and a right pointer. The left pointer points to the root of the left subtree. The right pointer points to the root of the right subtree, and the key contains the key value that's stored in that node. we augmented that information with an extra piece of information called the size. And remember that the size is the size of the entire subtree underneath this node. So if we augment the information with size, then it turns out that we can very efficiently solve both rank and select operation. Here is an example. I know it's not very clear on the screen, but be patient with me. So what you'll see here is that every node has a key value and a size information. Key value, size information, key value, size information. So the node at the leaf, this one here has value 3. And because the subtree beneath it has only one node to it, the size information stores 1. The other nodes here, you can see all the leaves here have size 1 because their subtree has only one node in it. If you look at this node here with 16, the key value is 16, but the size says 2 because the subtree beneath it has 2 nodes, both 16 and 14. Same thing with 19, it has 19 and 20 in its subtree. Same thing with 7, it has 2 and 1, 7 and 3 in its subtree. Then there are other nodes. This guy has 4 as its size, this guy has 7 as its size, this guy has 12 as its size, and the root of the tree has 20 as its size, and that's because there are 20 nodes in this tree. In general, the size information 20 can also be obtained by looking at the size of the left subtree, adding the size of the right subtree, 12 plus 7, and adding 1 extra for the root node, and that would give you 20. So 12 plus 7 is 19, 19 plus 1 is 20. Now, if you have this extra information stored in each node, it turns out that you can easily answer queries related to rank and select. So let me show you that in the next picture. Give me just a second. Okay. So here is the same red-black tree I showed you in the previous on a previous picture. So let's try and add some size information to this tree. So where would I put, which nodes would have size 1?
The leaves,
The leaves. So which would be?
the black ones.
So the black ones are really null nodes, and we're going to call those as size 0, just for the sake of argument. Okay. So really, the next level is where your ones are going to be, and those are the ones I've shown you. So anything with two of these null nodes as children would have size 1. Those are going to be the leaves of your tree. Okay. And as you go up the tree, you can figure out that you can simply add the sizes of the left and right subtree and get the size of these nodes. So where will you have 2? Which nodes will have size 2?
20, 71.
So 20 and 71. So anything where, so if you look at 93, this one is going to be 1 plus 1 plus 1, right? What about 52 or 76? What would be their sizes? They have children of size with numbers 2 and 1. So 2 plus 1 plus 1 will give you 4. Same thing here, 2 plus 1 plus 1 will give you 4. What would be the size of 85?
8.
That's right. So it's 4 plus 3 plus 1. And then up there at the top, it would be
13.
It would be 13. So those numbers shown there are the sizes of these various subtrees. And the moment you have these, it becomes relatively easy to figure out what the rank or the select operation will return for any given value. Okay. And we went through that last time. I'm not going to do it again. Instead, what I'm going to show you is something quite important. Remember, these rank and select operations, you need to be able to do this even after you do inserts and deletes. However, when you do inserts or deletes, we would not have updated the size information. So the question is, what do I do now? So the way this works is very simple. Let's say that you add a node down here. Let's say you add the number 53. Remember, 53 would get added somewhere here. If you add that node here, then that node will become size 1. As you traverse up the tree, each one will get increased by 1. So this one will become 2, this 4 will become 5, and this 13 will become 14. So all you have to do is to walk up the tree and add 1 to every node that you see along the path. And that'll take care of the size values. Same thing with delete. If you delete this node here, you decrease this by 1. So this node, of course, will be gone. This one will become 2 minus 1. This one will become 4 minus 1. This one will become 8 minus 1. And this one will become 13 minus 1. So inserts and deletes are easy to handle in the sense that not only will you be able to do those efficiently, but you can also update the size information quite efficiently. Of course, the code will take care of it, but this is important for you to understand why the augmented red-black trees are efficient. Another thing to understand is what happens when you do these rotations. Remember, we talked about rotations, and we saw how you can do either a left rotate or a right rotate. If you do a left rotate at this node 42, what will happen is that 93 becomes the parent of 42, and that's what you get on the, that's what you see on the right-hand side. 93 is now a parent of 42. And of course, the subtrees that hang off of it are now changing. This 6 remains in the same place. This 7 remains in the same place, but 4, instead of hanging off of this node with 93, now hangs off of 42. What's important to understand here is that the size information can be quickly changed, and it can be done efficiently, and you can see how this happens. To start with, this subtree here had 6 nodes, this had 4 nodes, and this had 7 nodes. So therefore, the size information here is going to be 4 plus 7, 11, plus 1, 12. And the size information here is going to be 12 plus 6, 18, plus 1, 19. Now, when you do the rotation, the trees move around a little bit, so you have to now update the size information. What is important to understand is that these 3 subtrees that are hanging off here, they will never change. Their size information does not change because you're rotating something up there. And so therefore, these numbers remain the same, but then this size information, instead of 19, will now become 11 because it's 6 plus 4 plus 1. And this guy here is now going to get the 19 from before, which is 11 plus 7 plus 1. So by changing the size information of just 2 nodes, I can fix the rotation very, very efficiently. And that's what is great about these red-black trees and the augmented red-black trees. I can do inserts, I can do deletes, I can do rotates, I can do, and thus maintain the size information. And once the size is maintained, I can do rank and select operations very, very efficiently. So now we are going to assume that this is a black box that we don't have to worry about, that we can manage a red-black tree as long as we keep the size information and then answer queries like rank and select in log n time. So now we're going to use that information to solve some problems. So that's where we're going to head next. If there are any questions, this is a good time to ask me.
Okay, I'm gonna ask a question. So the left rotation tree is like the opposite of the right rotation tree.
Repeat that, please.
can I state that the left rotation tree is the opposite of the right rotation tree?
Yeah, that's correct.
And the reason why I said that because like I see 92 being the parent, 92 being the parent for the right rotation tree, while the left rotation tree, 42 is the parent.
Correct.
42 is the parent, and 42 is the grandparent, while the right, while 93 is basically the child, and then the grandchild basically 6, 4, and 7.
That's correct. So you can, if you left rotate at node X and then right rotate at node Y, you'll get back the same tree.
Yeah.
Okay.
I see the argument. I see the argument.
All right. Okay. So any other questions? All right, good. So now you need to clear your head and start to think with me because we're going to try and solve a couple of nice problems. So let's start with this. I'm given an array of items, and I'm asked, I'll be remember the array has, let's say, n items. Then I'll be given a fixed range within the array, and I would be asked to find the largest item in that range. So, so let's say here is our array. I have 21, 9, 3, 6, 14, 11, and 7. You can see that it's not in sorted order. And I will be given indices. So I'm also showing you the index values up there. So this says if I ask you to find the largest item between 2 and 5, okay, so 2 and 5 goes through here. The largest item, of course, is 14. Instead, if I ask you what is the largest from 1 to 3, your answer would be 21. If I ask you what's the largest in the range 3 through 4, I have only 3 and 6, so therefore the largest is 6. If I ask you to find the largest from 5 to 3, this is not in the right order, so we're going to say this is undefined. This is a problem we want to solve. So our problem is that it's a dynamic situation. We don't really have the items in an array. We can store it any way we like, but it helps to think about this in terms of an array. And we are asking, if I go from the second item to the fifth item, tell me the largest value that you'll have. That's the kind of queries we're going to be asking. And occasionally we might insert things and delete things in this array. Does the problem make sense to you?
Yes.
Yes.
So we are given an array. Each array item has an index. That's the way we want to think about it, but maybe we don't want to store it in an array. That's up to you. But then I would be asking you lots and lots of questions saying, okay, tell me the largest between position 3 and position 7. And your job is to tell me that as quickly as possible. Now, the thing to figure out is, how do I make this task as efficient as possible, assuming that I ask you queries of this kind. I may ask you thousands and thousands of queries of this kind. So our job is to make each query as fast and as efficient as possible. Any suggestions for what we can do? What do you think is the fastest way to report the answers? Yes, Ricardo.
You can have like a tree. It's actually a data structure. It's a segment tree where the root is the maximum for the whole array, and then the left node keeps track of the.
Before you go forward, what would be the time complexity of the find max operation?
Log n.
Log n. Do you think you can do faster?
I know there's one answer for this. It's like DP, but it's not dynamic. So No, I don't know.
Remember, you are allowed to pre-process the data as much as you want. Okay, if you want to build a tree, that's up to you. If you want to build something else, that's up to you. But your job,
I was thinking about linked list. I was thinking of linked list.
your job is to answer these queries as quickly as possible. So my question is, what do you think is the fastest we can answer these queries?
O1, if you just store every single query, like from I to
Right.
J.
That's right. So how would I store every single query?
You keep a two-dimensional array.
Right.
And
Very good.
yeah.
So what we can do is we can anticipate every possible question. Remember, every possible question has a start index and an end index. We can put that into a large matrix, a two-dimensional matrix, where the rows correspond to the start index, the columns correspond to the end index, and the entry there tells us what is the largest item.
Yeah, but wait, wouldn't that like take O of n squared to update though?
That's right. Now, first of all, it's going to take us O of n squared to build that table. And if there are any changes, we're in trouble.
Yeah.
Right? So in that sense, it's not the best way to solve the problem. And secondly, we may not be willing to spend big O of n squared in order to pre-process the data. So we need a better solution. And Ricardo has proposed something to do with trees. So how do I build a tree? Now tell me, Ricardo, how do I build a tree?
So what you can do is you can keep track of, you have a tree starting at the rooted tree, and then the beginning node will give you the maximum query for the whole subarray, for the whole array.
Yeah.
And then the left node will give you the answer for an array from the left side all the way to the middle.
Yeah.
And then the right node of that root will give you from the middle +1 to the
Okay.
right side.
Yeah.
And then you can recursively build this.
Yeah.
So basically you answer every query.
But that'll only take care of queries that are either fully on the left side or fully on the right side. What do I do if it goes from left side to right side?
So first you build that tree, and then you can answer every query. You start off, this is basically like structured like a heap, I guess, because you can store it in an array.
Yeah.
But you have the left and then the right for the query, and then you start with 2 pointers. I think you start off with for the whole range for these 2 pointers.
Okay.
And then you find this recursively by finding the left answer and then the right answer, like the left subtree and the right subtree.
Okay.
If we go out of the ranges, then we just return like a really small number or.
Okay. All right.
And then
let me try and decode this for all the others here. Generally speaking, you're on the right track, and you probably will be able to figure this out. But for others, we need to think about this in a more structured manner. So what we're going to do is the following: we'd like to build a tree. This is really what we seem to be agreeing upon. Now, remember, if we build a red-black tree, for instance, we are able to efficiently do search, insert, or delete. Now, if we want to do search, insert, or delete, we want to know what is the key value based on which we build that tree. So the question is, what is the key value in this array?
Hello. Out.
You're gonna type it yourself, right over here.
Yeah.
What do you think is the key value?
I said 3.
Yes.
But less than I think 20. What's the thing? I think 21 will be the key value because 21 is literally like the value that's shared by 1, 3, 3, 4.
Yeah, Alec, hold on. That's not the right answer. Let me get it from someone else.
Oh, God.
what is the key value that you want to store in each node of the tree?
Would it be the index?
That's right. Why would it be the index?
Because our find max function is going to be trying to find within that range. So we
Well,
don't know.
It is the index. You are right about that. The reason it should be the index is because it's the index that's in sorted order. And remember, in a tree, when you go from left to right, you want things to be sorted. Yeah. For any node, you want on the left, in the left subtree, you want smaller values, and in the right subtree, you want larger values. Now, if you use the actual values that are shown in blue, that won't work out for you, because the left subtree may have 21 and 9, and the right subtree may have 11 and 7. That's not going to be going to give you this binary search tree type property. On the other hand, if you use the key value as the index, which is 1, 2, 3, 4, 5, 6, 7, then I could have the root as to be index 4, and on the left side to be all the things with lower index, and on the right side to be all higher index. That's why we want the key value to be the index. Okay. Now, if we make that the index, then it turns out that we can at least do search, insert, and delete, but then it'll only be with respect to the index value. It turns out that our queries are actually about the other value that we store. We'll call that not the primary key, but we'll call that the secondary key. So each value, each node will now have both a primary key and a secondary key. The primary key, as I said, is the index, and the secondary key is the value that we stored. And remember, the value is what we showed here. The first row of this array is the index, and the second row is the value. Is that clear? Everyone okay with this?
Yeah, that cleared up.
Okay.
Cleared
So
up.
now let's see what this begins to look like. This is our array, and those are the kinds of queries we want to start. We want to answer. So now let me show you what the tree will start to look like. Here's what I'm going to do. I'm going to take all the values and put it in the leaves. Okay. And then I'm going to take a pair at a time, and I'm going to build the next level of the tree. And then I'm going to take again a pair at a time and build the next level of the tree all the way until I build the entire tree. So what you'll see here is that, where's my mouse? Yeah. So the first two items with index 1 and 2, they have values 21 and 9. And they are connected to their parent, and that parent now has information about the range 1 through 2. The items 3 and 4 have a parent that represents the range 3 to 4. These two guys now have a parent that go all the way from 1 through 4. And then finally, the root of the tree has a node that represents the entire tree or the entire list. Does that make sense to you?
Yes.
So in each node now, I have both the primary key, which of course is just the index value, and I have a secondary key, which is the actual value that's stored in that node. Okay. And remember, because it was not an even number of items, I had to have a null node here. But now comes the interesting part. As I go up the tree, I always keep track of the largest item in this entire sublist. So in the sublist of 1 through 2, the largest is 21. In the sublist 3 to 4, the largest is the maximum of 3 and 6, which is 6. In this node, it's 5 through 6, and the largest is larger of 14 and 11, which is 14. And finally, over here, it's 7 and null, the largest is 7. Is this clear?
Yes.
And then when I go to the next level, all I have to do is to compare two things, the values from the two children, which tell you that that's the largest value in their subtrees, and that's the value that gets pushed up. So the maximum of 21 and 6 gives you 21, maximum of 14 and 7 gives you 14, and the maximum of 21 and 14 gives you 21. So if somebody asks you what is the maximum in 1 through 7, all I have to do is to go to the root of the tree and I would have the answer. What we're going to do next is to figure out how to find the maximum for any given range. And here we have to get into some of the details that Ricky was mentioning. But this gives you, the way it's shown here, gives you a better way to organize the data so that you can then answer your find max queries more easily. Is that clear?
Yeah.
All right. So where were we? Yeah. So now the question is, how do I do the find max query? So this is what the data structure is going to look like. And in order to build this tree, by the way, all you have to do is to start with the list and take two at a time and build the leaves. Once you build the leaves, then you build the next level of the tree, and then the next level of the tree, and then the next level of the tree, all the way until you get to the root. Is that clear? Do you think you can handle this? You can write code for this? Maybe?
Maybe.
I think I can. I think I can.
Okay.
I've been studying binary history for the last 2 weeks.
Very good. Very good. Yeah. All right. So now let's figure out how, once the tree is built, how we're going to answer the queries. That's our big challenge next. Okay. Are you ready for this? All right. So let's see what happens. Yeah. So let's say we are given an arbitrary range, I comma j, and we're asked to find the largest item in this range. There's our array again, and those are your indexes, and that's your tree. That's what it looks like. So our question is, if you give me some strange looking range, how do I figure this out? Well, in general, the way we're going to go about this is we're going to start at the root and ask if that range is exactly what's in the root. If it's 1 through 7, then we are done. If it's not, then we'll check whether it's in the left subtree. If it is completely in the left subtree, we'll just go there and figure things out. If it's completely in the right subtree, we'll go there and figure out, and we'll be done. The problem is if it starts in the left subtree and ends in the right subtree, that's when we're going to have some trouble. And that's what we are going to look at next. Is this part clear to everyone?
Yes.
All right. So question is, how do I do this? Well, so let's go from 3 all the way to 3 to 6. Let's try 3 to 6. Let's say I is 3 and j is 6. For 3 to 6, we know the answer. We can look at this array and we know the answer should be 14. And the question is, how are we going to figure out this 14, given that we only have this tree that we want to work off? So first of all, if I is 3 and j is 6, it's definitely not the one in the root. It's 3 to 6 is definitely not completely in the left subtree, so that's not going to work out. 3 to 6 is not completely in the right subtree, so that also is not going to work out. So it's partly in the left subtree and partly in the right subtree, and then we have to put these results together. So what we're going to do is the following. Because we know that the midpoint for this, the breakup of the left subtree and right subtree is right between 4 and 5. So 4 is on the left subtree and 5 is on the right subtree. So what we can do is we can take our 3 to 6 and break it down from 3 to 4 and 5 to 6. Is that clear? So then we're going to find the largest in 3 to 4. We're going to find the largest in 5 through 6, and then take the larger of the two. Eventually, we'll work our way, we'll figure out that 3 to 4 is part of 1 to 4. In fact, it's in the right subtree, and so we'll go down there, and there we'll figure out that 3 to 4 is exactly what's stored here. So we know that the answer is 6. So from the left side, we would get an answer of 6. From the right side, again, we know we want to figure out 5 through 6. We'll go down and it'll tell us that it's completely in the right subtree. Then here it'll tell us that it's completely in the left subtree. And here it'll tell us that it's exactly what's stored here and that the answer is 14. So this guy will send 14 all the way up. This guy will send 6 all the way up. And the largest would be 14. If you compare 6 and 14, 14 is larger. And so then we would report the answer 14, which would be the right answer because from 3 to 6, the largest is 14. Now let's try something a little more complicated. Let's, instead of going from 3 to 6, let's go from 2 to 5. If we're going from 2 to 5, we know that the answer should still be 14. Okay, but let's figure out how we are going to walk down the tree and figure out this answer. Any questions about this so far? All right. So remember, I is 2 and j is 5. We want to go from 2 to 5. Is that clear? Okay, so we start with 2 to 5 up here. We know 2 to 5 is contained in 1 through 7, but we have to figure out whether it's completely in the left subtree or it's completely in the right subtree or partly in the left and partly in the right. So 2 to 5, we figure out that it's not completely in the left subtree, it's not completely in the right subtree, it's partly here and partly here. So we break the range 2 through 5 into 2 through 4 and 5 through 5. Okay. So if we do 2 through 4 and 5 through 5, then 2 through 4 is part of this range 1 through 4, but it's not in the left subtree, not in the right subtree. So it's partly here and partly here. Same thing with, with 5 to 5, we know it's completely here. We also know it's completely here. We also know it's completely here. And so the answer for 5 through 5, the largest value in the range 5 through 5 is 14. So from the left side, we get 14. Now, from the right side, we get 14. We have to figure out what happens on the left side. Remember, the left side, the range is from 2 through 4. So we come down, 2 through 4 is part of this, but it's partly here and partly here. And so we break it down into 2 through 2 and 3 to 4. 3 to 4, of course, the largest is 6. And 2 through 2, we walk all the way down and figure out that the largest is 9. So the larger of 9 and 6 would be 9. And that would get passed up. On this side, we got 14. And the larger of 9 and 14 is 14. And so the answer we would report as 14. And what you'll see is that all of this is very similar to what we did with the rank and select. We figured out how to walk down the tree and compute the answer. Is that clear? Well, yeah. This is hard, so please ask questions.
How do you know when you need to split it at a node?
Yeah, that's good. So for that, you have to walk down to the left subtree and figure out what its range is. So if you're looking at 2 through 5, you look over here, and this says that the highest on the left side is 4. So immediately you know that 2 through 4 should be one part, and then 5 onwards should be in the other one. Is that clear?
Yeah, so if you know if the range you look at the left and the right, and you know if it's split, then you have
Yeah.
to go down the left and then down the right and then compare.
Yeah.
But if you know if it's only on the left or only on the right, you just take that route, right?
Correct.
Okay, thank you.
So let's say we want to do 2 to 3. Okay. So if I just want to go 2 to 3, what do? I start over here. 2 to 3 is completely contained in 1 through 7. Is it contained in 1 through 4?
Yeah.
Yes. So 2 to 3 is contained in 1 through 4. So we forget about the right side now. Then we go down here and then ask the question, is it completely contained in 1 through 2?
No.
It's not. Is it completely contained in 3 to 4? Again, the answer is not. So we have to break it. And we break it right there because we know that 1 through 2 is on this side, 3 to 4 is on the other side. So we're going to break it into 2 through 2 and 3 to 3. And 2 to 2 is completely contained here, and 3 to 3 is completely contained here. So then we restart the process, and 2 through 2, when you do it, you know that it's not on the left side, it's on the right side, and this is exactly 2 through 2, and this side here is exactly 3 to 3, and so you compare these 2, 3, and 9, and that would give you the answer, and the answer would be 9 is the largest. Is that clear?
Yeah, thank you.
Any questions about this? I know it's a little bit challenging here, but all of this works with the magic of trees. And if you understand these trees, then everything is going to be good for you. What we've shown here, is that a binary search tree? What do you think? Is it a binary search tree?
I'm thinking yes, because by the indexes it is.
Right. So if you think of each node to have a primary key to be an index, then it is. Okay. So ignore all these other numbers that are here. Think of this as, think of the primary key to be the midpoint where you broke this. So think of the primary key here to be 4.5. Okay. Think of the primary key here to be between 2 and 3, so 2.5. Think of the primary key here to be between 6 and 7, so 6.5. So if you think about it that way, then this whole thing looks exactly like a binary search tree. Okay. So we've used the index of the items as the key and then broken it down, even though we've written down a range. I could have written it down as a single item, and that would be the point that splits the left side and the right side. So if I did that, then I could write 4.5 here, 2.5 here, 1.5 here, 3.5 here, 5.5 here, and 6.5 here, and here it would just be 7. Does that make sense?
And
So-
I have a question about that.
Uh-huh.
So if our range was from 2 to 5,
Yeah.
so and together that's be 7, and then we're to divide that by 2, that's be 3.5, right?
So if the range is from 2 through 5,
Mm-hmm.
It doesn't all fit in either the left side or the right side. So here it would be 2 through 4, and here it would be 5 through 5.
But can we, so from 2 to 5, the middle is 3.5. Can we use that value to search in this tree, or do we have to use I and J?
No, what you would do is the following. Here, imagine that you're storing in the root the number 4.5, which is the split point. So you would look at 2 through 5 and you would say, is that value 4.5 completely outside of this range on this side, or completely outside the range on this side, or in that range? So if it were larger than 5, then you would then only go and search in the left subtree. If it is smaller than 2, you would only go and search in the right subtree, and so on and so forth. Does that make sense?
Okay. Yeah. Thank you.
Okay. So organizing the tree this way turns out to be fairly easy because of the way you can build the tree. You can, start to pair things and build a parent node, take the next pair, build a parent node, take the next pair, build a parent node, and then take these nodes here and start to pair them and build parent nodes. So building this tree is really not that complicated, but once you do it, then the code for figuring out the find max is for that you just have to go and change the original code for either rank or select. Okay. How else can I make things clear for you? Because I know it's a little heavy here. This stuff is not that easy. Samara, David, questions?
Oh, really quickly, I mean,
Yeah.
okay, so the two conditions that we have for, like, I guess returning is when it's either completely in the range or it's like not in the range at all, right?
Yeah.
Okay, so like if we were going like I guess going back to like the range from like 2 to 5. So let's say we were looking at 1 and then 2. So one would return so it was, I think, something like what Ricky was saying earlier. 1 would like return a very small number since it's like out of the range, and then 2 would return 9 since it's completely within the range. That's like, yeah. And then we would start building up our solution from there, right?
I'm not following you. Start again.
Okay.
Which
So
part are you are you in the part of building the tree or doing the find max?
Oh, doing the find max within the
Okay,
range.
so you've already built the tree then.
Yeah, the tree is already built.
Okay, now what?
Okay, so now, like, let's say it was like going back to the example, I'm just like making sure like I'm solid on this. Yeah, so like let's say we were trying to find a range between like 2 to 5.
Okay.
Yeah, and so we like, I guess, first start on the finding the largest on the left side. And
well,
so
you're rushing. So you start with 2 through 5 and you start at the root of the tree because that's all you have access to.
Yeah.
Okay.
Sorry. Yeah.
Then you compare over here and this guy will tell you whether to go left or to the right or to do both.
Okay.
And that depends on whether your 2 through 5 is completely on the left side, completely on the right side, or spans the middle.
Okay.
Are you following this?
Yes.
Okay. So 2 to 5 is not completely in the left side because 1 through 4 and 2 to 5 are not exact. One doesn't contain the other, right?
Right.
Same thing with 5 through 7. 2 through 5 and 5 through 7 are not exactly compatible. So that means that 2 through 5 is partly in the left and partly in the right.
Right.
So that's why we have to break this up. The question is, where do I break it up? Well, for that, the two children will give you the clue for how to break it up. The left child goes from 1 through 4. The right child goes from 5 through 7. So therefore, that's where you break it up. So your search range is 2 through 5. And so therefore, you're going to break it up between 4 and 5. So then 2 through 5 becomes 2 through 4 and 5 through 5. Is that clear?
Yes.
Okay. Now we have two separate ranges. One you will search on the left side, and one you will search on the right side. You'll find the largest in each one of them and then put it all together at the end.
Okay.
Okay.
Yeah.
Now 2 through 4, you're going to search in the left subtree. 5 through 5, you're going to search on the right subtree. So let's focus on one of them because they're similar. So how do I search for 2 through 4 in 1 through 4 in the left subtree? So remember, the root of the left subtree has a root that says 1 through 4, right?
Right.
But we want just 2 through 4, not 1 through 4. So the question is, should I now search in its left subtree or in its right subtree? So I'm here, I need 2 through 4, and I'm asking, should I go here or should I go here? And again, you see that it doesn't belong on either left or right. So part of it goes from 2 through 2 on the left side, and then from 3 to 4 on the right side.
Mm-hmm.
Is that clear?
Yes.
Okay. So that's how you keep going further and further down, and ultimately you'll have the answer.
Okay.
Should I finish up and go all the way for you? Or
No,
you-
no, I'm good now. I see it. Yeah.
All right. Okay. Others? Questions? Okay. All right. So we have about 10 minutes, and I'm going to tell you about a slightly harder problem. Okay. That's why it's important that you understand this problem of find max before we go there. Are there any questions about this find max? Don't be shy. Okay, then you're ready for the harder problem. So here the problem is slightly different. This time you're given an array just like before. And again, we'll put down some indexes just to make things clear. But in this array, there are going to be lots of repeats, and it's all in sorted order. Okay. So I have 2 1s followed by 4 3s, and then a 6, and then 3 9s, and then a 15, then 3 24s, and a 39. And I'm going to ask you the query. I'll give you a range. I'll say 6 through 14. And your job is to tell me what is the most frequent item in this range. Is that clear? Is the problem clear?
Yeah.
Yeah.
So I should probably do an example. Let's do an example. So what is this? What is the most frequent item from 6 through 14? So there is only 1 3, only 1 6. There are 3 9s, and there are 3 24s. So it doesn't matter which one you report. It's either a 9 or a 24. Both of them have frequency 3. Is that clear?
Yeah.
If I go from, say, 3 to 10, what's the most frequent item?
3.
It's going to be 3 because there are 4 3s and only 3 9s. What if I go from 4 through 9?
3.
Still go 3. What if I go from 5 through 10?
9.
9.
This time it'll be 9, and so on and so forth. So you get the idea, right?
Yeah.
Okay, now how do I approach this problem? Can I do this with the same kind of trees that we had before?
Yeah.
All right, so give me some ideas. What should I do?
So we still want the range, but instead of
Yeah.
keeping track of the max, could we use a hash table and then store the values in the range with their frequencies as.
No hashing. We won't do hashing.
Oh God. Okay.
Um,
We want to use trees because we want to use what we learned very, very recently. Hashing can solve it, but there are some serious challenges, and I'll show you why.
mm,
So you're going to soon get the idea here. So let's say that, well, we saw this, we know that from 1 through 5, the most frequent item is 3. From 5 through 10, we know the most frequent item is 9, and so on and so forth. So let me show you what the tree looks like now. Here are the items, and here's the index. What if I squished this array and I wrote it down in the following manner? I have a value 1 which occurs twice. I have a value 3 that occurs 4 times. I have a value 6 that occurs only once. I have a value 9 that occurs 3 times. A value 15 that occurs once, and 24 that occurs 3 times, and 39 that occurs once. So now I've created a new array which only has unique items, but with each one, it has a frequency. Do you think this will help you?
Yeah.
Go on, tell me what to do next. We have about 7 minutes left. Think of a tree and think of what you want to put in as its primary key and what you want to put in as a secondary key.
we still want to do put in the index as the primary key, right? Then
remember, your original array now is sorted.
oh, it's sorted. Oh, okay. Then that wait, you can just put the element and then
Which element?
the array element.
Okay.
And then
Yeah, and then
would it be, would the other key be the frequency?
Okay, very good. Yeah. So it turns out that you could use instead of using the index, you could use the actual value now as the primary key and use the frequency as the secondary key. Okay, so here's my tree again, right?
Right.
So now I have value of 1 and frequency of 2, value of 3 and frequency of 4, value of 6 and frequency of 1, and so on and so forth. Okay. When I put them together, what happens on the next level? What are these values now? How do I get that?
The one that has a greater second number.
Right. One that has a greater frequency. And so this guy here has a frequency of 2. This guy has a frequency of 4. So it must be that one. This guy has a frequency of 4. This guy has a frequency of 3. So this must be frequency 4, right? And similar things happen here. 24 has a frequency of 3. 39 has a frequency of 1. So it must be 24. Are you with me?
Yeah.
Yeah.
Right. So now I have the same looking tree, right? except that the index now, I can also store the index. By the way, I can store a whole bunch of different information, right? Here I'm storing that the whole array is here, 1 through 15, and I've broken it at 10, or between 10 and 11. And on this side, from 1 through 10, 3 is the most frequent item, and its frequency is 4. Okay? On this side, I have 24. Of course, it goes from index 11 through 15. So it goes from 11 through 15 from here to here. The 24 is the most frequent item, and its frequency is 3. So now I want you to think about how you're going to do find most frequent item from anywhere to anywhere. Should we try and figure this out? Should we go from, say, 7 through 14? Actually, let's do something easier first. Let's do 7 through 10. If I want to do 7 through 10, and I ask you what is the most frequent item, I'm going to start here.
9. Would that be 9? Because like there be 3 9s right there. Then we come from 7 through 10. That means like you have 1, 2, 3 9s.
I'm going to start here.
That means that'd be 3.
I'm going to start at the root, and the root has the range of 1 through 15. And then I will ask the question whether 7 through 10 is completely on the left side, or completely on the right side, or partly in both. So 7 through 10 is completely on the left side because it's contained in 1 through 10. So I just move down there. Then again, I ask the question, is it in the left subtree or the right subtree? And again, I figure out that it's in the 7 through 10 is completely in the right subtree. And then here I see that it's in the root. And so I can simply answer the question as 9 is the most frequent item and its frequency is 3. Is that clear?
Yeah.
So this was the easy case. Let's do something slightly harder. Let's go from 7 through 14. When we do 7 through 14, we know that it's not in the left subtree, it's not in the right subtree, it's partly here, partly here. So we've got to break it down to 7 through 10 and 11 through 14. And then 7 through 10 will bring us here, 11 through 14 will bring us here. Then these two answers we would compare. 9 has a frequency of 3, 24 has a frequency of 3. Since they are both equal, we'll just report one of them. Okay. The harder part is if we are inside one of these groups. So what if I go from 4 through 13? If I go from 4 through 13, which is the most frequent item? So it goes from here, 4 through 13. Okay.
Yeah, that'd be 3. Because there's 4 3s in this inside. But
Alex,
I need to figure out.
Alex, hold on. Your job is to figure it out from the tree, not by looking at the array. So
Okay.
we're going from 4 through 13, and we start at the root here, and we know that 4 through 13 would require a search on both sides, and we would break it down into 4 through 10 and 11 through 13. 4 through 10 would also figure out that it's partly here and partly here. We would break it down through 4 through 6 and 7 through 10. And this side, we will break this down into 11 to 13. Then we would go down. Ultimately, we would have an answer from here because we would go down from 4 to 6. We would look down here, and we know that 4 to 6 is basically a bunch of 3s. And because we've broken down that list, we know that the frequency of 3 is not 4, but it's only 3 because we're only looking at part of that array. So there's some extra work that we have to do, but we can figure out what those highest frequencies are, and then work our way back up the tree to figure out the answer. Does that make any sense?
Yeah.
A little bit harder.
Yep.
But it's doable. Any questions? I'm just out of time, so I just have time to answer some questions.
What if it wasn't sorted?
If it was not sorted, then it would be very, very challenging. If the, for instance, if the threes are not together, then there's very little hope of doing something smart like this. Then we would have to go back to your hashing, Lazaro. Even that would be challenging because the threes could be all over the place. By the way, question for you. Do you want, you know that there's this practice session from, what is it, 2 to 5? Do you want, do you also want some mock competition problems?
I say yes.
What we can do is I could give you the same problems you had last time where you had trouble, but now that you know more, maybe you could try a couple of these problems. I could also change, put some slightly easier ones and see if you could work something out. Would you like that?
Yeah. Well, can
Yeah.
you also send us the slides from last week? Because I was using a red black tree some code I found online.
Okay.
But I'm not totally sure if that was correct.
Okay.
And I know you provided a repo with good code.
All right. I will send you all the slides today.
Thank you.
All right. Shall we stop here? Are there questions? All right, guys. Have a good day.